The graphics cards sitting on your desk today might be rendering games at a fraction of their true potential, yet the visuals sprawling across your monitor look impossibly sharp and fluid. This contradiction defines modern gaming, where artificial intelligence has begun rewriting the rules of performance itself. AI upscaling technologies are fundamentally reshaping how we experience video games, making unprecedented visual quality accessible to hardware that, by traditional standards, shouldn't be capable of delivering it. For decades, the gaming industry operated under a simple equation. Better graphics required more powerful hardware. Gamers chased the latest processors and graphics cards, accepting that cutting-edge visuals came with a premium price tag and a seemingly endless upgrade cycle. But neural networks developed by tech giants like Nvidia, AMD, Sony, and Intel have disrupted this paradigm entirely. These aren't incremental improvements or minor optimizations. They represent a fundamental shift in how games are rendered and displayed in real time across PC gaming platforms and next-generation consoles like the PlayStation 5 Pro. The appeal is strikingly straightforward. Experience games at resolutions and frame rates previously thought impossible for your hardware. Imagine running the latest 888 blockbuster at near 4K resolution with frame rates exceeding 140 frames per second, all while your GPU operates at a fraction of maximum capacity. This isn't science fiction or distant possibility. It's happening right now in gaming setups worldwide, quietly transforming expectations about what constitutes adequate performance. The technology accomplishes something counterintuitive to conventional understanding. Rather than simply stretching pixels or blurring edges as older upscaling methods did, AI upscaling intelligently reconstructs images by predicting missing visual data. Neural networks trained on millions of high-resolution images learn patterns of how pixels should transition, how light should reflect, how details should appear at various scales. The system renders games at lower native resolution, then leverages artificial intelligence to intelligently fill in missing information, creating results that rival native high-resolution rendering while consuming a fraction of the computational resources. The sophistication deepens further with frame generation technology. Advanced AI systems don't merely upscale static images. They can synthesize entirely new frames between traditionally rendered ones, effectively doubling or tripling frame rates without rendering those frames conventionally. A game running at 60 frames per second becomes 180 frames per second through intelligent interpolation, dramatically enhancing smoothness and responsiveness. Several competing technologies dominate this landscape. Nvidia's DLSS leverages specialized tensor cores within their GPUs to deliver superior image reconstruction and frame generation capabilities. AMD's FSR takes an open source approach, offering compatibility across a wider spectrum of graphics cards regardless of manufacturer. Intel's XeSS provides competitive functionality through Intel Arc GPUs, or legacy support via DP4A instructions. Sony developed PSSR specifically for PlayStation consoles, debuting with the PS5 Pro and representing a significant competitive advantage for their ecosystem. The results appear almost absurd in their effectiveness. Games rendered internally at 1080 or 1440 resolution look genuinely indistinguishable from native 4K rendering to the human eye. Benchmarks consistently demonstrate frame rate improvements ranging from 2 times to 4 times native performance with minimal or imperceptible visual degradation. Some users report they cannot detect any difference whatsoever between upscaled and native rendering. This technology arrives at a critical moment in gaming's evolution. Traditional graphics rendering struggles perpetually to meet escalating demands for higher resolutions combined with ray tracing, advanced physics simulations, and ever-increasing graphical complexity. The hardware bottleneck has become severe. Achieving native 4K or 8K resolution with full ray tracing pushes even the most expensive graphics cards to their absolute limits, often at the expense of frame rates. AI upscaling breaks this deadlock entirely. It democratizes high-fidelity gaming experiences, extending the lifespan of existing hardware and reducing pressure on consumers to constantly upgrade their systems. The implications ripple across the entire gaming industry, affecting how developers design games, how manufacturers prioritize hardware development, and what gamers reasonably expect from their equipment. Before we continue exploring the profound implications of this technology, subscribe to the channel and tell us in the comments where you are watching from. The technological breakthrough that makes AI upscaling possible emerged not from gaming necessity alone, but from decades of research in machine learning and computer vision. Neural networks required enormous training datasets, specialized hardware accelerators, and algorithmic innovations that only became viable in the past few years. Before this convergence, the gaming industry operated under a performance ceiling that seemed immovable. For generations, the fundamental bottleneck remained consistent and brutal. Rendering games at native 4K resolution with advanced visual effects demanded exponential increases in computational power. A game running at 1080 resolution with ray tracing might require a graphics card costing $500. Achieving the same game at native 4K resolution with comparable quality demanded hardware costing $2,000 or more. This relationship created a harsh reality where the latest gaming PCs became prohibitively expensive for average consumers, and console manufacturers faced impossible decisions about pricing and performance targets. The pixel problem extended beyond mere resolution numbers. 4K displays contain over 8 million individual pixels, each requiring calculation of color, lighting, reflections, shadows, and countless other properties for every frame rendered. Rendering this many pixels 30 times per second, let alone 60 or 120 times per second, demands extraordinary processing power. Ray tracing, a technique that simulates realistic light behavior by calculating how rays bounce throughout virtual environments, multiplies computational demands by orders of magnitude. Combining 4K resolution with full ray tracing on consumer hardware became essentially impossible without accepting unplayable frame rates in the range of 20 to 30 frames per second. This created a perpetual treadmill where gamers constantly chased hardware upgrades. The industry conditioned consumers to expect that beautiful games required new purchases every few years. Graphics card manufacturers benefited from this cycle, releasing increasingly powerful and expensive products. Console generations spanning 5 to 7 years meant that early in a generation's lifespan, hardware could deliver cutting-edge visuals, but by generation's end, performance seemed inadequate compared to newer titles' demands. Previous attempts at solving this problem through traditional upscaling offered only compromises that exposed their fundamental limitations. Checkerboard rendering, used in some PlayStation 4 games, rendered alternating pixels and attempted to reconstruct the missing information through simple mathematical algorithms. The results looked acceptable on television screens at distance, but revealed artifacts and detail loss when examined closely. Dynamic resolution scaling, where games reduced resolution during intensive scenes, created jarring visual transitions and inconsistent image quality. Neither approach truly solved the underlying problem, they merely managed failure more gracefully. What distinguished these historical attempts from modern AI upscaling was their reliance on mathematical rules rather than learned patterns. Traditional upscaling algorithms followed explicit programming instructions, stretch pixels in certain ways, average neighboring colors using specific formulas, apply predetermined filters. These approaches had theoretical limits built into their design. They couldn't truly reconstruct missing information because they lacked understanding of what the missing information should represent. Neural networks revolutionized this paradigm by learning from examples rather than following programmed rules. By analyzing millions of image pairs, low-resolution versions paired with high-resolution originals, neural networks developed intuitive understanding of how visual details should appear at different scales. The system learned that smooth gradients should remain smooth when upscaled, that sharp edges should maintain definition, that textures should display appropriate complexity. This learning-based approach could discover patterns that explicit programming never could. The infrastructure enabling this shift arrived simultaneously from multiple directions. Graphics card manufacturers began integrating specialized tensor processing cores, hardware specifically optimized for the matrix operations fundamental to neural network computation. Data centers provided training resources allowing researchers to develop and refine these models at scale. Cloud gaming platforms created demand for efficient rendering techniques that reduced bandwidth requirements. Gaming studios accumulated technical expertise with machine learning implementation. By the early 2020 decade, all necessary components aligned simultaneously. The hardware existed, The algorithms were sufficiently sophisticated, the software frameworks had matured, and the market demanded solutions to an increasingly acute performance problem. Suddenly, what seemed like distant research became practical, deployable technology ready for real-world implementation in millions of gaming systems worldwide. Neural networks possess a fundamentally different capacity than their predecessors. Rather than relying on handcrafted algorithms or simple interpolation methods, these systems learn to reconstruct images by understanding underlying patterns in visual data. When a game renders at 1440 resolution internally, AI upscaling doesn't merely enlarge the image, it intelligently predicts what details should exist at 4K resolution based on learned knowledge of how textures, lighting, and structures typically appear. The mechanism operates through layers of mathematical operations inspired by biological neural networks. Each layer processes information differently, progressively refining the upscaled image. Early layers might detect edges and basic shapes. Middle layers recognize textures and materials. Deeper layers understand complex relationships between objects and their environments. This hierarchical processing allows the system to make contextually appropriate decisions about what pixel should display where, creating results indistinguishable from native rendering in most scenarios. Frame generation represents an even more dramatic capability. Rather than simply upscaling spatial resolution, advanced AI systems generate entirely new frames between traditionally rendered ones. A game rendering at 60 frames per second becomes 120 frames per second through AI interpolation. The system analyzes motion vectors and temporal patterns, predicting how objects will move between frames. This technique introduces apparent fluidity and responsiveness that dramatically enhances gaming experience, particularly in fast-paced titles where frame rate stability defines playability. Nvidia's deep learning supersampling, or DLSS, pioneered mainstream adoption of these techniques. The technology leverages specialized tensor cores built into their graphics processors, hardware specifically designed for accelerating neural network computations. Different DLSS versions demonstrate evolving capabilities. Early iterations focus purely on spatial upscaling, while recent versions incorporate frame generation achieving triple-digit frame rates from previously unachievable performance levels. DLSS integration into major gaming titles created immediate performance benefits, allowing gamers with mid-range hardware to experience visually demanding games at previously impossible frame rates and resolutions. AMD's Fidelity FX Super Resolution approaches the same problem from a different architectural perspective. As an open-source solution, FSR achieves broader hardware compatibility, functioning across AMD, Nvidia, and Intel graphics cards. This democratization of upscaling technology meant developers could implement resolution-agnostic solutions benefiting users regardless of their specific hardware manufacturer. AMD's approach trades some quality characteristics for universal accessibility, making advanced upscaling available to a wider audience. Intel's Xe supersampling entered the competition more recently, leveraging their XMX cores integrated into ARC graphics processors. For users with older graphics hardware lacking dedicated AI acceleration, XeSS implements fallback code paths using standard GPU instructions, ensuring broader hardware support at the cost of reduced performance compared to dedicated tensor implementations. This strategy positioned Intel as the inclusive option for upscaling adoption. Sony's PlayStation Spectral Super Resolution represents console-specific optimization. Rather than licensing external technology, Sony developed proprietary upscaling algorithms specifically tuned for PlayStation 5 Pro hardware architecture. PSSR demonstrates the potential advantages of vertical integration. Custom silicon, optimized drivers, and software specifically engineered for particular hardware can achieve superior results compared to general-purpose implementations. PlayStation 5 Pro launch titles showcased PSSR delivering native 4K image quality from 144 resolution internal rendering, while maintaining 120 frame rates in supported games. These implementations share a seemingly absurd characteristic that nevertheless reflects genuine technological achievement. Games running internally at quarter of 4K resolution, or even lower in some cases, appear to players as authentic 4K experiences. Side-by-side comparisons between native 4K rendering and AI upscaled lower resolutions often reveal negligible visual differences, yet the upscaled approach consumes dramatically less computational power. Performance metrics demonstrate 2 to 4 times frame rate improvements across supported titles, with visual quality metrics showing minimal degradation compared to traditional rendering. The implications extend beyond mere performance numbers. These technologies represent a fundamental shift in how the industry approaches the eternal tension between visual fidelity and rendering efficiency. Where previous generations accepted this as an immutable trade-off, AI upscaling suggests entirely new possibilities for optimization. The implications extend beyond mere performance numbers. These technologies represent a fundamental shift in how the industry approaches the eternal tension between visual fidelity and rendering efficiency. For gamers, this shift translates into tangible, life-changing benefits that reshape how they experience interactive entertainment. Consider the practical reality facing millions of PC and console players worldwide. A gamer who purchased their graphics card 3 years ago suddenly discovers their hardware now performs as if it were state-of-the-art through no physical upgrade whatsoever. AI upscaling extends the effective lifespan of gaming systems dramatically, deferring the expensive necessity of hardware replacement. Where previous technology cycles demanded costly upgrades every 18 to 24 months to remain competitive, AI-assisted rendering potentially extends that window by years. For console owners, this means their PlayStation 5 or Xbox Series X remains relevant and capable of running next-generation titles at high visual fidelity well beyond typical hardware generational boundaries. The responsiveness and immersion of the gaming experience itself improves substantially. Frame generation technology eliminates the stuttering and input lag that once plagued demanding games on moderate hardware. A player in a competitive first-person shooter notices immediate responsiveness improvements when their graphics card can smoothly maintain 120 frames per second rather than struggling to achieve 60. This responsiveness translates directly into competitive advantage and significantly enhances casual enjoyment of story-driven experiences, where smooth presentation creates psychological presence within the virtual world. For game developers, AI upscaling liberation manifests as unprecedented creative freedom rather than spending development resources optimizing every asset for specific hardware constraints. Teams can focus on artistic vision and gameplay innovation. Developers can implement complex ray tracing effects, dense geometry, sophisticated physics simulations, and expansive environments, knowing that AI optimization will handle the challenging details of delivering this content efficiently to diverse hardware configurations. A single game version can scale seamlessly from entry-level hardware up to high-end systems, expanding potential audience size and eliminating the need for separate optimization efforts across multiple target platforms. The hardware industry experiences seismic shifts in how performance itself becomes defined and valued. Previously, specifications centered on raw computational throughput measured in teraflops and gigahertz, metrics that directly correlated with rendering capability but provided little information about actual player experience. AI upscaling inverts this assumption. A graphics card with dedicated tensor cores for neural network computation becomes more valuable than a card with higher traditional compute specifications but inferior AI acceleration. Manufacturers now compete on AI silicon efficiency rather than pure computational brute force. This paradigm shift drives innovation toward entirely new categories of specialized hardware previously considered niche or unnecessary. The investment by major technology companies underscores how fundamentally transformative this shift appears. Nvidia, AMD, Intel, and Sony collectively commit billions toward developing, refining, and deploying these technologies. Such investment only flows toward capabilities that fundamentally reshape market dynamics and customer value propositions. The competitive intensity surrounding DLSS, FSR, and XESS implementations demonstrates that AI upscaling represents not an incremental improvement, but rather a generational leap in graphics technology importance. Yet alongside these transformative benefits emerge legitimate concerns requiring thoughtful consideration. Frame generation occasionally introduces visual artifacts in edge cases, moments where the AI system produces slightly incorrect predictions about how objects should interpolate between traditional frames. Certain fast-paced action sequences occasionally manifest subtle ghosting effects where motion predictions diverge slightly from actual rendering results. These artifacts represent not failures of the technology, but rather inevitable limitations of predictive systems operating under computational constraints. As AI models grow more sophisticated, such artifacts diminish further. Yet they highlight that AI rendering occupies an uncanny valley between traditional rendering and perfect visual fidelity. Input latency considerations emerge as particularly important in competitive gaming contexts. Adding AI prediction layers theoretically increases processing time between player input and visual feedback. Modern implementations minimize this concern through careful engineering and low latency prediction models, yet the concern persists that future implementations pushing AI capabilities further might sacrifice input responsiveness on the altar of visual perfection. Developers must carefully balance these competing demands. The emergence of AI-assisted rendering fundamentally redefines what performance means in modern gaming. Historically, the gaming industry measured performance through raw computational metrics, teraflops, clock speeds, memory bandwidth, numbers that described hardware capabilities but often bore little relationship to what players actually experienced. A graphics card might boast impressive specifications, yet fail to deliver smooth frame rates or visual quality in demanding titles. This disconnect between specification and experience created perpetual confusion among consumers and frustrated hardware makers tasked with justifying expensive investments. AI upscaling inverts this traditional measurement paradigm. Performance now encompasses not just raw rendering power, but the intelligent application of neural networks to maximize visual output from available computational resources. A modern gaming GPU with dedicated AI acceleration cores might deliver superior real-world performance than a theoretically more powerful card lacking such specialization. This represents a seismic shift in how the industry evaluates and values hardware capabilities. Manufacturers now compete fiercely on AI silicon efficiency, tensor core architecture, and machine learning optimization, rather than engaging in raw teraflop comparisons. The benchmark that matters has fundamentally changed. Next-generation gaming consoles will embody this transformation most visibly. The PlayStation 5 Pro already demonstrates how dedicated AI hardware becomes central to console design philosophy rather than peripheral enhancement. Future iterations, whether subsequent PlayStation systems or next-generation Xbox hardware, will allocate increasingly substantial silicon to AI acceleration capabilities. These machines will prioritize neural network compute above traditional graphics processing, a reversal of historical design priorities. By the time the PS6 arrives, AI rendering might constitute the primary performance path, with traditional rasterization relegated to supporting role. This evolution reflects a profound realization that intelligent optimization delivers more meaningful performance gains than incremental increases in raw computational throughput. The implications ripple far beyond gaming hardware into broader real-time graphics applications. Virtual reality experiences stand to benefit enormously from AI frame generation, where smoothly interpolated motion becomes critical for preventing motion sickness and maintaining immersion. Augmented reality applications, which layer digital elements onto live camera feeds, gain the ability to render complex visual effects without overwhelming mobile processors. Professional visualization tools in architecture, engineering, and medical imaging can deliver previously unattainable real-time performance on standard workstation hardware. The techniques pioneered in gaming begin infiltrating every domain where real-time visual fidelity matters. Perhaps most speculatively, AI rendering capabilities suggest possibilities for generating missing environmental details in real time. Current systems focus on reconstructing existing scene information at higher resolution or interpolating between rendered frames. Future iterations might generate entirely novel geometric details, textures, and environmental content based on learned artistic styles and contextual understanding. Imagine a game world where distant mountains, individual leaves on trees, and architectural details emerge dynamically from AI generation rather than pre-authored assets. This capability would fundamentally alter game development workflows, shifting effort from asset creation toward training neural networks and establishing artistic parameters. This trajectory raises intriguing questions about the nature of visual experience itself. If players cannot distinguish between traditionally rendered pixels and AI-generated content, does authenticity matter? When neural networks become integral to the rendering pipeline, do artists lose creative control or gain liberation from tedious technical constraints? These philosophical questions lack simple answers, yet they become increasingly urgent as AI systems assume greater responsibility for visual presentation. The long-term implication suggests a future where hardware performance plateaus not through technological limitation, but through sufficiency. The raw computational power of graphics hardware in 10 years might barely exceed today's capabilities, yet games look and perform dramatically better because AI systems wring exponentially more visual quality from the same hardware. The heavy lifting of visual fidelity transfers from silicon to software, from physics to intelligence. This fundamental reorientation transforms not just gaming, but our entire approach to real-time graphics, suggesting that computational efficiency and intelligent systems matter more than ever-increasing raw power. AI upscaling represents nothing less than a fundamental revolution in how gaming performs and evolves. This technology transcends incremental improvement, marking instead a watershed moment where the essential nature of rendering itself undergoes transformation. Players experiencing contemporary titles with upscaling enabled encounter visual fidelity that simply would not exist without neural network intervention. The distinction between rendered and AI-generated pixels becomes increasingly irrelevant when the human eye cannot distinguish between them. Yet this transparency masks profound shifts occurring beneath the surface of gaming hardware and software philosophy. The accessibility revolution unfolds most powerfully at the consumer level. Gamers who invested in mid-range graphics cards or aging console hardware suddenly discover their devices capable of delivering experiences previously reserved for enthusiasts with premium equipment. This democratization of visual quality fundamentally alters the gaming landscape. Players no longer face the tyranny of perpetual hardware upgrades to maintain visual parity with cutting-edge releases. A graphics card from several generations past, augmented with capable AI upscaling, delivers experiences comparable to substantially more expensive modern alternatives. This shift extends gaming lifespans, reduces financial barriers to entry, and allows hardware manufacturers to focus engineering efforts on efficiency rather than relentless power escalation. Developers liberate themselves from the traditional constraints that define game design priorities, creating visually stunning worlds at native 4K resolution while maintaining competitive frame rates historically required extraordinary engineering compromises or simply proved impossible within realistic production budgets. AI upscaling dissolves these constraints. Development teams can now pursue artistic visions with unprecedented ambition, implementing complex ray tracing, volumetric effects, and environmental detail that previously demanded prohibitive computational investment. The freedom extends beyond mere visual polish into gameplay possibilities, where responsive systems and complex simulations become feasible on broader hardware platforms. Artists and designers gain liberation to prioritize creative expression over technical limitation circumvention. The philosophical implications deserve serious consideration. Gaming has always occupied an interesting space between artistic medium and technological showcase. AI upscaling tips this balance decisively toward art. The technology enables creators to emphasize narrative, atmosphere, and imaginative vision rather than wrestling with hardware constraints. Yet this liberation carries philosophical weight. Questions emerge about authenticity when neural networks generate pixels that humans cannot distinguish from traditional rendered content. Does artistic intent remain pure when machines predict and generate visual information? These are not merely academic concerns, but deeply relevant to how future creators approach their craft and how audiences relate to the experiences they consume. The gaming industry's competitive dynamics have fundamentally reorganized around these technologies. Hardware manufacturers now differentiate through AI silicon efficiency and neural network performance rather than raw computational throughput alone. Nvidia's continued dominance stems not from incremental GPU improvements, but from tensor core architecture uniquely suited to machine learning acceleration. AMD's competitive positioning relies on delivering AI performance at lower price points through aggressive optimization. Intel's re-entry into discrete graphics depends entirely on competitive AI rendering solutions. Sony's custom PSSR implementation represents strategic differentiation in the console market. This reorganization reveals that the future belongs not to the most powerful hardware, but to hardware most intelligently optimized. Looking forward, the trajectory becomes increasingly clear. Next-generation consoles will allocate silicon predominantly to AI acceleration, making intelligent rendering the foundational performance paradigm rather than supplemental enhancement. The PlayStation 6, whenever it arrives, will likely feature more transistors dedicated to neural network compute than traditional graphics processing. This represents a complete inversion of historical console design philosophy. By 2030 or 2035, native rendering might constitute merely one component of comprehensive AI-assisted visual pipelines where frame generation, upscaling, and content synthesis form the dominant performance architecture. Beyond gaming, these techniques propagate into virtual reality, augmented reality, professional visualization, and real-time rendering applications across industries. The techniques proven in gaming become infrastructure for broader technological domains. Medical imaging gains unprecedented real-time interactive capability. Architectural visualization delivers immersive experiences on consumer hardware. Augmented reality applications overlay complex effects without overwhelming mobile processors. This technological inflection point marks a transition where computational sufficiency becomes achievable not through ever-increasing raw power, but through intelligent allocation of existing resources. The future of gaming performance lies not in the next generation of silicon breakthroughs, but in deeper integration of artificial intelligence into every rendering stage. Neural networks have fundamentally transformed what performance means, what is possible, and ultimately how interactive entertainment will evolve for generations to come.